Okay, welcome to part 2 of today's lecture. As we were going to our break, we talked about some of the mistakes that were made just trying to do this problem. And one of the common mistakes is when you go through and you do your limiting reactant, you find the moles of each one, and then you divide by the coefficient, you get this number out here. Well, this number out here really isn't anything. This is your moles of silver nitrate here. This is just to kind of get the ratio, dividing by 1, dividing by 2, to find out which one you have the most of or the least of, to determine your limiting reactant. So you always want to use this moles here of 0.0294. You don't want to use this. Now, if you do use the 0.0147, you can use that. You've already divided by this 2. So you just leave that off, so you would just take 0.0147 times 2 times 85, and you get your answer. I highly recommend you use the mole value. And that's why it's important to label what you're finding here so you know what it is. Okay? So that's just a common mistake that students make using this method. So use your mole value. All right, there's that. Now, today we're going to continue on and talk about stoichiometry, but into solutions. Almost every reaction that we do takes place in some kind of aqueous solution. So we have to know we have to know how many moles of our solute are present. So stoichiometry and solutions. Okay, so let's just do a little review of solutions. What makes a solution? What are the two parts? Solute and solvent. So solute plus solvent yields a solution. Now again, just to clarify, which one is which? If I put sugar into water,
the sugar is the solvent.
And the water is, okay, so if you didn't hear that, sugar is the solute, water is the solvent, okay? The thing you're dissolving is the solute, what you're dissolving it into is the solvent. Together, they make a solution. Later, we'll talk about the different ways it dissolves and the whole dissolving process. But for right now, we're going to be measuring the solute and the solvent going to a solution. So the most common way of measuring concentration is going to be molarity, which is a capital M. Anybody remember what the definition of molarity is? Remember doing it. Actually, this might have been virtual. I think we might have done solutions virtually last year, which makes it mean that you just didn't really learn much. Last year's virtual wasn't in the spring.
You mean for pre-AP time?
For pre-AP.
Oh,
Yeah,
we're all seniors.
All seniors. All right, so you learned as senior, then it's just gone. Okay, regardless. All right, molarity is defined as moles of solute divided by liters of solution, not a solvent. It's the total volume. So most of the time you can just put a solid into a liquid, but the solid will occupy some of the space and make the volume of the solution a little bit greater. Okay? So it's always going to be liters of solution. So if we have something that's moles per liter, what does that make a conversion factor between? Not a hard question, no. Which is what unit? Liters. And what? And moles. Whatever the two units are on your number, that's a conversion factor between those two units. Density is grams per milliliter, or grams per cubic centimeter. It's a conversion factor between grams and cubic centimeters, a mass to a volume. The molar mass is grams per mole. So it's a conversion factor between grams and moles. Anytime you have two units, it's a conversion factor between those two things. Which tells me that if I know how many liters of a solution or milliliters that I have, then I'm going to be able to know how many moles if I know the molarity. I can just multiply. The molarity, and this is something you just need, this is super important, times volume always equals moles. Because it's moles per liter times liters, it'll leave you moles. Okay, so it's pretty straightforward. So the first thing we have to do is be able to know how to calculate molarity given just information, and it's going to be a pretty simple calculation. And then we can use that once we have it. Again, the first step of stoichiometry is take grams to moles, take atoms to moles, take whatever the given is to moles. So now if we're given a solution volume, so many milliliters of 3 molar NaOH, we can then convert that to moles using the given molarity. It's actually going to be easier because the molarity is going to be given. You won't have to calculate the molar mass, okay? So you just know how to use that conversion factor, okay? Now, we generally don't go and measure out moles. What do we measure out? Grams. And how do we change grams to moles? So, a more workable form of this is grams over molar mass divided by liters. So if we're going to calculate the molarity of something, most of the time it's going to tell me how many grams are given, convert it to moles, and then divide by the volume and go to liters. So, now we're going to take a quantum leap to chapter 13. Trying to do this without glasses on. Okay, so I'm moving now to page 568. Making a big jump in the textbook. And I mean, if you want to look it up, you can, but I mean, it's going to be right here. Now, there's all different ways of calculating concentration. We're not going to get into all those because they don't make us do them anymore on the AP test. So we're looking at number 43. Well, actually, we'll do 44 because then you can go back and do 43. The answer's in the back of the book for 43. Okay? So if we look at number 44, am I out of the screen?
Yes, you are.
Just move it to try to get me in there, please. 44, see if you can get both. No?
Yeah, I got it.
Okay. What is the molarity of each of the following solutions? So 15 grams of aluminum sulfate in 250 milliliters or 0.250 milliliters of solution. Okay? So again, it's just going to be molarity is grams over molar mass over liters. So I have 15 grams of aluminum sulfate divided by the molar mass of that thing. Okay, somebody just, if you have a calculator out, I'll call numbers out to you. Okay, 12 times 16, 12 times 16, and then 3 plus 3 times 32.1 plus 54. 3. Okay, so that really is telling me how many moles I have. Not many. Okay, does everybody understand that part? We're good? Divided by Now we get to do the metric conversion. 0.25 milliliters is going to equal how many liters? What are we going to do with the decimal here? All I heard was a mumble.
Maybe 3 times. 250.
Dude, it's going to be 250 liters?
Yeah.
Milliliter is smaller than a liter.
0.000.
It's going to be 3 zeros. Now, is this zero significant?
Yes.
Yeah, you would not put that zero unless you measure to that degree of accuracy, because it doesn't change how big or small the number is. So therefore, I need to keep that zero here, liters. So on your calculator, you can just go 15 divided by 342.3 divided by 0.000250 equals
I got 175.
175.
Yeah.
That's huge, but that's very, very, very concentrated solution. But look, it's only in 0.25 milliliters. I really probably think that they meant to say 250 milliliters on this one, or 0.25 liters. Make it come out more like 0.175 molar, because I've never seen a solution 175 molar. Okay? But I knew that when we had 0.25 milliliters, it was going to be not a whole lot of solution. All right. So B is a good one, because what type of compound is this? What do we call this? A hydrate. And how did you know that, Ann? The dot 2H2O, right? So we'll talk about how we do the molar mass of that one. So this is A. B. Again, the molarity is going to equal 5.25 grams. Now, again, I'll call out some numbers, but we need to make sure we pay attention to how we calculate the molar mass of this. So I'm going to go 6 times 16, so 96 plus 28.02 plus 90 is 52, but 54.94. Chromium is 52.
178.96.
Okay?
Make sure you don't include the water.
Oh, shoot. That's the whole point of this. So how do we include the water? Do we go times? What do we do? You add. So water's 18.02 times 2 is 36.04. So we add the 36.04. I'm really starting to worry myself here.
You do 215.
215.
That's it.
Really? Comes out exact?
Yeah.
Okay, so we have to add in some sig figs there. If the calculator drops it off, that means it goes right to a 0. So you have to then put the zeros back in. Your calculator doesn't generally do sig figs. There was one version of a calculator that kids had, I think it was like the TI-89 Platinum, that did sig figs. It would do it for you, but your calculator will drop off those zeros at the end, even though they're significant. All right, divided by what's the volume? 175 milliliters is going to be how many liters? 0.175. Okay, so the only thing that I really wanted to point out that I totally screwed up was calculating the molar mass of a hydrate. We add the water, so it's the 178 plus 2 times 18.02. So you add that all in. Okay. All right. So what does this all come out to? 0.140 molar, and that is MnNO3 2.2H2O. Now, just to review naming, Mn. Everybody know what Mn is?
Manganese.
Manganese, okay? Mg is magnesium, Mn is manganese, okay? Now manganese, remember when you have a transition metal with more than one oxidation state, we have to use a Roman numeral. Manganese has 5 different possible oxidation states, okay? So with the 5 different oxidation states, to try to figure it out, which one do you think it's in? How do you know that, Ben?
Because the charge would be 2,
Because the reverse crisscross, because when we write the formula, we bring whatever the charge is down here. This is a 1. We know nitrate's -1. We bring that there. We don't write the 1. So I know that this is +2. So I'm going to say manganese 2 nitrate. Then what? Think about the lab.
dihydrate,
Say that again, Paul.
dihydrate,
Dihydrate. Manganese 2 nitrate dihydrate. This is how we're going to do naming all year long. I'm just going to kind of keep throwing it out there for you. We're not going to take a test on it and whatever, but just kind of keep reviewing the rules as we go. Okay? So, when you have a transition metal with more than one oxidation state, now how are you going to know if it has more than one oxidation state? For right now, for us, we're just going to look, and if it's got more than one number above its symbol, then yes, it has more than one oxidation state, so you need a Roman numeral. Notice silver does not, cadmium does not, so you don't have to say silver 1 nitrate, you can just say silver nitrate. It's only when it has more than one oxidation state. All right, so calculating molarity is very straightforward. Okay? Now, notice here on this dilution problem, the next one. Okay? So let's just throw this in right now. This is going to be more notes. What does it mean to dilute something? If you dilute your Kool-Aid, what do you do? Make it less tasty, but how do you do that? You add water, right? Or more solvent. Okay? So you're changing the concentration by adding more solvent. The question is, how much more do you have to add and going, when you're diluting this? So when I'm looking at here, 35 milliliters of 9 molar H2Os is diluted to 0.5 liters. Okay? This is just going to follow a proportion. And so we're going to have a simple equation that says the molarity of the concentrated times the volume of the concentrated is always equal to the molarity of the dilute times the volume of the dilute. C equals concentrated, T equals dilute. Anytime you have a dilution problem, anytime you're mixing 2 solutions together to get the new molarity, you just take the concentrated, that's going to be your original, and then the diluted is going to be what you end up with. So the concentrated one is always the thing you start with. In this case, we're starting with 9 molar, 35 milliliters of 9 molar. The good news on this is that you don't have to change to liters because it's a ratio, so if you use milliliters here, you use milliliters there. You divide by 1,000, divide by 1,000, you're going to get the exact same answer. Okay? So you don't have to change, you can use any volume units you want on this. It doesn't matter as long as they're the same on both sides. So we have 9 molar times 35, right? Is equal to, we're looking at the question asked for what's the molarity of the dilute, and we're changing it to 0.5 liters. So notice you're just going to really go, I'm making another mistake. Why can't I just divide by 0.5? It's not, you got milliliters here, and I was going to liters here. Okay? They have to be the same unit. Now you can take the milliliters to liters, or you can take the liters to milliliters. I'm going to take milliliters to liters to milliliters and say 500 milliliters. Okay? So the molarity, the dilute, is just going to be 35/500ths of what it was before. Because we diluted it from 35 milliliters to 500, so it's just going to be that ratio. So if you double it, you know, you go from 1 liter to 2 liters, your molarity is going to be half. It's always a ratio of the volumes. And what does that come out to? 630 molar. So we diluted it from 9 molar to 0.63 molar. Now, if you're ever mixing gasoline with oil, or you're mixing bug spray, the concentrated bug spray, or Roundup, or they're going to spray in a bug sprayer, you're really doing this because they say use 1 teaspoon or tablespoon per gallon of water, or a cup per gallon of water. They're getting you to dilute it because they've given you a concentrated version, and you're diluting it to a useful, less dangerous concentration. Now, they're just not telling you, you know, what the molarity is, but somebody in a factory did the calculation and said, okay, well, if we make it this strong, this is how much water we have to add to get it to the concentration that we need to do whatever the thing is designed for. Okay? So, dilution. As soon as you see anything about dilution, molarity, MCVC equals MDV. That's the equation. All right. Last thing. Let's use molarity now in stoichiometry. Here's a good question, number 4083. It says some sulfuric acid is spilled on a lab bench. You can neutralize the acid by sprinkling sodium bicarbonate on it, which, by the way, is a lab safety technique that if you ever spill it, you just get some baking soda, sodium bicarbonate, and just sprinkle it all onto your acid until it stops bubbling. Then you know all the acid's been neutralized, and it's safe to clean up, and you just put it in the trash. Okay? And so, we actually have, well, I have to do this a lot in labs because things get spilled throughout the year when we use strong acids. Okay? So all of this is nice information, but not all that important. Okay? So here's the reaction that takes place. Now again, remember, the hydrogen is the bi. So the real name of this is sodium hydrogen carbonate. Okay? I don't know where the bi for hydrogen comes from, but that's what it stands for. Sulfuric acid. And how do I know that this is an acid? So what? H is at the beginning, right? Anytime you have hydrogen, any hydrogen plus any anion is going to be an acid. Okay? And then that's where we go to acid nomenclature. 8 goes to ic. So if it's sulfate, it's sulfuric acid. If it's sulfite, it's sulfurous acid. 8 goes to ic. Ite goes to us, O-U-S. Okay? Then if it was just binary, if it was just H2S, we'd say hydrosulfuric acid. Okay? And we'll talk about that again, but that's neither here nor there for this. So sodium bicarbonate is added till the fizzing due to the formation of CO2 stops, which is how you do it. So 27 milliliters of 6 molar. So now I'm given a volume and a molarity. With spill, what is the minimum mass of sodium bicarbonate? Okay? So now I know that I have 27 milliliters, and it says it's of 6 molar of this, and the question asks for how many grams of that. That's how I like to give them. I like to just put it in my balanced equation, just what am I given, what am I looking for? Well, I know my mole ratio is 1 to 2. Okay? But again, that's a mole ratio, so I have to get this to moles. So how do we say we got this to moles? What times what equals moles? Go back and look at your notes. What times what equals moles? Molarity times volume equals moles. That's going to be our conversion. So now notice again, 6 molar is really 6 moles per liter. Capital M stands for moles per liter. So this is my complicated, or my unit, my number that has 2 units on it, versus 27 as milliliters. I didn't do it right. It just says 27, not even 27.0. Okay? I only have 1 unit on this. That's what I'm going to start with. Okay? But I know that molarity is in moles per liter, so I've got to change this to liters. So how do I change that to liters? Divide by 1,000, which means I'm going to move the decimal 3 places. So again, you do that in your head. Liters of H2SO4. Okay, you don't show work for that, you just do that. You don't have to, divide, hopefully you know, divide by 3, you're going to move the decimal 3 places. Okay, so now instead of using my molarity and not having grams here, instead of using the molar mass when I have grams, I'm going to use the molarity because I have moles per liter. Where does liters need to go? So it's going to be 6 moles over 1 liter. So I just have my new conversion factor. Now, if I stop right there, what do I know? Moles of H2SO4. Now I'm just like any other stoichiometry problem. So I need to get to moles of sodium bicarbonate, so what's the next step? Mole ratio. 2 moles NaHCO3 for every 1 mole H2SO4. And then lastly, how do I go to grams? Molar mass of my my unknown. 48 and 12 is 60, 61, 23 makes 84. And this is 23.99, that's an 01, so it should come out, it's 01, 84.01 is what I say it gets. So you would need 84 grams of sodium bicarbonate to neutralize 27 milliliters of 6 molar H2SO4 that got spilled. At least 84 grams. I always just sprinkle a whole ton on it and have excess.
Wouldn't you need to multiply that?
Yeah, I think
That's
you
not
need
the
a
case.
multi,
I wrote it. I said it, didn't I?
yeah. You did.
I'm starting to scare myself here. I said it, and that's the right answer when you multiply it, but I just didn't write it out. And I ended up saying 80, what was the molar mass? 0.1. I can't believe I didn't write that. In my brain I wrote it. And that came out again to, do we not multiply that out?
6.8 is
6.8. Is that what you're saying?
yeah.
8 what? Oh, there's only 2 6 bigs because of 27, you're right. Let's try that again. Alright, so all that means is that you guys are going to really have to stay alert because I'm screwing up all the time and keeping me honest. Yeah, I swear I know how to do all this. I'm just getting messed up. Alright, so the whole thing is with stoichiometry with solutions, you just use the molarity. And the molarity is almost always given. If it's not given, we just calculate it easily with grams over molar mass over liters, and we figure out what the molarity is, then use that as our conversion factor between moles and liters. Super easy. Okay? Since we have this few minutes left, see you do number 84 then. A little bit of a twist, but it's the same idea. I'm going to give you this. What's the mole ratio between the acetate ion, which is this is your vinegar, okay? The distinctive odor of vinegar is due to acetic acid, which reacts with sodium hydroxide according to the following, okay? And there's really supposed to be an H there. CH3COOH plus NaOH. So there's a typo there. That there's supposed to be an H in that equation. Okay, but what's the mole ratio between those two? 1 to 1. So when we talk about the equivalence point, that's when moles of this equals moles of that. Okay? So, what can we find? What's the question asking for? I have 3.45 milliliters of vinegar. And it needs to react with 42.5 milliliters of this, and it's 0.115 mole. What's the question? How many grams per quart? Right? What do we need to find first? Well, we don't even have to go all the way to molarity. What do we want to go to? Grams. Okay, you can go to molarity, and then from molarity kind of go the rest of the way, but we can just go straight to grams. Then we have to change milliliters to quarts using our conversion factor over here, right? And then just grams per quart. So again, we have to know what we're looking for. Read the question. How many grams of acetic acid are in 1 quart? So I need grams per quart. So I got to figure out how to get all of this information to all equal that. Well, I know molarity times volume equals moles. It's 1 to 1, so that's going to be moles of acetic acid. Well, then how do I go moles to grams? Molar mass. So then I have grams. I'd stop there. Then I do separately, I do the conversion, 3.45 milliliters, change that to liters, change that to quarts, and then divide. Okay? Start with what's given. Know what you're looking for. See if you can finish that up now in 4 minutes. It's a Monday math fun. We'll go over this first thing tomorrow.
Do we turn it in or do we just?
Yeah. Is it not going?